Next up on track 1, we have Martin McKeaveney going through DynamoDB. And on track 2, we have Kubernetes from, apologies, my memory's not as good as Mark's, James Glennon. So enjoy.
So thanks very much for tuning into this talk about NoSQL databases in general, and more specifically DynamoDB. So the NoSQL debate, we're going to talk a bit today about how NoSQL databases work and why they're maybe thought about in the wrong way and maybe approached in the wrong way. And we'll be using Dynamo as a case study throughout. A bit about me, my name is Martin McKeaveney. I'm a software engineer and co-founder of Bodybase, a no-code startup based here in Belfast. So first off, what is DynamoDB? DynamoDB is a fully managed, multi-region, key value and document database providing single-digit millisecond latency at almost any scale. And one thing that's important to note there is the key value and document thing. It's not just for direct key value lookups on single symbol types, but we can have more complex types in there as well. So before we get into any of the DynamoDB stuff, I just want to go back a little bit and talk about databases in general and their kind of progression through the years and how we've got to this point. So relational databases are the natural place to start. Relational databases are a wonderful technology. They're pretty simple to pick up. They're extremely common and they're super flexible and pretty much the default choice for pretty much most applications nowadays. And their flexibility comes through the use of joins. So you create your data in different tables. You might have a students table and a classes table. And then whenever we query that database, it finds the rows in each table, scans them and decides which ones to join together and then returns them to the client. So one of the other features of relational databases is referential integrity. And essentially that lets us make sure that our data stays, we have good integrity of our data. So in that student and classes example, we can't delete a class that has a bunch of students. We can't add a student to a class that doesn't exist. So it's good in that way. It's also very vertically scalable. It's always easier to bump up your database instance and add more memory and CPU. On the other hand, the part that makes relational databases flexible and powerful is also its bottleneck when it comes to performance. Joins can be very costly and very unpredictable at scale when it comes to performance. As your data set grows or you've got lots of different queries running at the same time against the database, things can start to get slow. And it's quite hard to plan ahead for this. You can create indexes and things like that, but it's almost impossible to plan for scale with relational databases in some cases. SQL queries are also boundless, so there's no limit as to how many rows can be scanned as part of a query. And that's not just your results, you can limit those, but you can't really limit how many rows get scanned. So it's very easy to write a very bad SQL query that can use a ton of memory and CPU and potentially crash your database server. Also, horizontal scaling is quite hard. Horizontal scaling is easy whenever you can set it up in such a way where a single request gets served by a single node or partition. This is very hard to do in relational databases, and you usually find that data, you're jumping about from left and right and paying the cost of network latency. So over the past sort of 2-3 decades, NoSQL databases have become quite a big thing. And they were essentially invented to handle the scale and throughput that SQL cannot. There's no concept of joins in NoSQL databases. They've kind of done away with that whole thing because it is the bottleneck after all. Data is segmented into different partitions and it makes it easy and fast to access it at large scale. And one of the things that NoSQL databases are optimized for is CPU. Back when relational databases were invented, storage was the most expensive thing in the data center. That's no longer the case, it's now compute. So NoSQL databases optimize for this and it makes sense. So how does a NoSQL database work? This is the architecture here of a Dynamo table, but it really applies to most NoSQL databases. They're pretty much all set up this way. And really, they use partition keys or segments to decide which node is going to serve which request based on the data that you're inputting or reading from the database. So in this example here, we've got the DynamoDB request router and a few nodes. And you can see that these nodes have a particular set of user IDs that they're responsible for. So like, 1 to 300 or so. And then whenever we go to write some data into there, it checks the partition key, in this case 741. And based on that, it decides which node it's going to be stored in. So why is this useful? It's useful when we try to read data out of the database. So when we try to read out the user ID of 741, the DynamoDB request router knows which node to go to. And this is good. This means that we can scale almost infinitely and just keep creating more and more little partitions and nodes. And based on that key, we then know which node is going to serve which request based on those keys. So one thing that is very, very common for people who are making transitions from relational databases to NoSQL is they try and apply what's known sometimes as faux SQL. And that's they try and apply relational patterns to data in NoSQL databases. And that doesn't work very well, and it certainly doesn't scale. So flexibility is one thing that is brought up quite often when it comes to NoSQL databases. But really, it's more of a sales pitch. They're not really meant to be like that. It's not meant to be schemaless, add whatever schema you want. It's not meant to be like that. It's actually extra work up front, and you need to define your access patterns if you want your NoSQL database to scale. It's a pretty easy way to think about it when it comes to NoSQL versus SQL databases and where they're applicable at large scale is the difference between an OLAP and an OLTP system. An OLTP system, or an online transactional processing system, takes transactions and writes them in real time and stores them. An OLAP system, or an online analytical processing system, runs analytical queries and on historical data generated by OLTP systems. So OLAP systems are a better fit for SQL because you need that flexibility. You need to be able to do aggregations and roll-ups on that historical data, whereas OLTP is generally a pretty good fit for NoSQL. And if you find yourself trying to use a NoSQL database, doing tons of different tables, loads of joins, and writing all that yourself in your own code, there's no point in that. SQL databases are optimized for this and have been for decades. So, it's quite obvious when you need to use a relational database or when you're using a NoSQL database wrong. So, with that said, DynamoDB. So, originally, Amazon.com was run on a full Oracle infrastructure with Oracle databases, and they eventually reached a bit of a sort of tipping point with this. Even though they had access to some of the premier experts with Oracle databases, Oracle themselves, for example, they started to hit bottlenecks, as you could imagine, at that kind of scale with Amazon.com. So what they realized was most operations were actually key value operations, over 70% in fact, and they were operating on single values, or if it was over multiple rows, it was in the same table. So Amazon decided to go off and build their own database to solve this problem. They went and built Dynamo in-house, and they released the paper in 2007 after they'd implemented it themselves for Amazon.com. And the paper had some really highly novel and influential ideas around distributed systems and NoSQL databases, and it influenced quite a few other offerings, like Cassandra from Facebook. Amazon then took that Dynamo service and wrapped it up in a managed package that they deployed on their AWS platform in 2012. Since then, Dynamo now serves well over 1 trillion requests per day, and it's used by companies all over the world, from multinational conglomerates to small startups. The likes of Lyft use it to store GPS locations for their rides. Tinder uses it to store millions of user profiles and billions of matches. BMW use it for cars as sensor services. Under Armour use it to support their fitness community of over 200 million users with the MyFitnessPal app. And Toyota Racing use it for real-time decisions on pit stops and other racing data, as well as 100,000 other AWS customers. So why is it so popular, and why is it growing so fast? There's a couple of benefits to using DynamoDB. One is that it's durable and highly available. As we saw earlier, it splits data into different partitions or nodes, and these nodes are then replicated across availability zones. So if there's a natural disaster or something goes wrong, you won't lose access to your data. It's highly performant for the same reason. We're able to partition data and understand which request gets routed to which node, and it keeps things very fast. It's fully managed. You don't need to worry about scaling things up and down. You don't need to worry about managing infrastructure. That's all done for you. It has adaptive capacity. It's able to scale up and down, or you can actually set up how much usage you think you're going to use and have significant cost savings because of that. It's also able to adapt in the sense that as your data starts to grow, it'll split off into more and more nodes and more partitions, so you don't end up with enormous partitions and damaged performance. Access control, we have pretty highly granular access control at the table, attribute, and even item level. So that's good for security purposes. And we have the concept of bounded queries. As we talked about earlier, relational databases don't have this. They have bounded queries in DynamoDB. So if you request a result that's over 1 megabyte, it'll actually give you a pagination key back, and you have to paginate through that in the client. So it won't let you request a huge amount of data in one go. DynamoDB essentially won't let you write a bad query. And by bad query, it means a query that won't scale. So let's dive into the basics, the basic building blocks of Dynamo. The first is tables, and they'd be familiar to anyone who's used relational databases. They're just a grouping of data records, users, dogs, cats, whatever it may be. We have items, and an item is a single data record in a table, and they're uniquely identified by a primary key, and we'll get into that in just a moment. So you can see here we've got a user record with a primary key of user ID, and they're just like rows in SQL. We have attributes, and attributes are pieces of data attached to a single item. They must have a type, so there's scalar types like string and number. There's document types like maps and lists, and then we have sets, which are just sets of multiple scalars with no duplicates. So you can see here an attribute, one example is an age, and these are like columns in a relational database. So primary keys, there's two types of primary keys in Dynamo. There's a simple primary key, which is just a single attribute, and that attribute gets used as the partition key. So you can see here, like the user ID example, that's a simple primary key. We have then a composite primary key, which is made up of two different attributes. So we need to make sure our primary key is unique, and in some cases a partition key alone isn't enough to make it unique. So in this case we have a partition key of product ID, and we have two items with the same product ID, so we need another attribute to make it unique. In this case we add another attribute called the sort key, and then that's used to distinguish uniqueness between records. So you can see that the ones with the same partition key have a different sort key and therefore are unique. And this becomes very handy in future when you're trying to query on a partition key. You get the sort key attributes sorted automatically for you, and that comes in quite handy. So let's dive into an example. Pretty much everyone here has probably taken their car through an MOT at some point. And the MOT, for those who don't know, it's basically like a checkup for your car once a year to make sure that it's roadworthy. And you get a letter in the post, you get told which centre you're going to go to, and they have these big gates, and you get told which gate you need to go to and at what time. So we'll use this to, as an example, and start to model an MOT appointment system using DynamoDB. So first off, we'll create a table. We create an MOT appointment table, and we need a composite primary key. The partition key is a centre gate, so Belfast gate 3, for example, and then that's not enough to distinguish uniqueness. Lots of cars might be at Belfast gate 3, so we need another attribute to make it unique, and that's going to be the time. So we make the time the sort key. So after we've created our table, we can start to put some records or items in there. We put an item that's Belfast gate 2 at a certain timestamp, and then we say the make and model. And in Dynamo, you'll notice we didn't put down what our fields were apart from the partition key and sort key. Dynamo doesn't care about that; it only cares about your keyed attributes. So you can add as many other attributes as you want. So we put in this item, and the router then knows which node it's going to go into. This is a bit of an oversimplification, but it would put it into a node based in the partition key, so in this case Belfast 2. We then start to add some records in there, so we'll add some MOT appointments for Belfast gate 2 at a certain time, and Newton Ards gate 1, and we'll start to add some extra items in there. So if we want to query these out then, and say, give me all the MOT appointments at the Belfast Test Centre at gate 2, ordered by time, all we have to do is ask for the Belfast 2 partition key, and it'll give us all the items that are partitioned by Belfast gate 2, and organized and sorted by time ascending. So you can see how we can write simple, easy queries by keying things properly and knowing our access patterns up front. So this is how you would actually express this using the AWS SDK in JavaScript. And you can see here how we have a function to query our items. We pass in our table name, which is MOT appointment. We have expression attribute names and expression attribute values, which are really just the keys and values that get interpolated to the key condition expression, which is the query itself. So you can see here that we can just query the items by querying by the partition key, Belfast 2, and that'll give us all the MOTs and the Belfast Test Center, Gate 2, organized by time. So before we dive into a more advanced example, there's a couple of other concepts to understand about Dynamo that come in useful. One of which is consistency. So consistency is a very common topic in distributed systems. There's strict consistency and eventual consistency. Strict consistency means that data will always be up to date. You'll never have anything stale. Whereas eventual consistency is that there's a potential that you might get stale data even if it's only for a short time. Dynamo by default is eventually consistent. Usually the data is updated within half a second or so. But sometimes if you do a write and read instantly, you might get stale data in that case. But in a lot of systems, that doesn't really matter all that much, unless you're talking about bank transactions or something that relies very heavily on strongly consistent reads. Twitter feeds or social media feeds or anything like that. It doesn't really matter if you get data that's half a second stale. So where this comes in important is when it comes to cost. In Dynamo, you don't pay for an instance or a size of an instance. You pay for how much you read and write. So we have read request units and write request units. A read request unit that uses a strongly consistent read uses 1 unit, whereas an eventually consistent read uses half a request unit. So it's actually double the price to use strongly consistent reads. A write request unit, it uses 1 to write an item up to 1 KB. And uses more for anything over that. So you want to make sure you're not putting huge amounts of data in with your writes. So querying Dynamo. In the previous example that we saw, you can only query index data in Dynamo, and we did that. We queried by partition key, where you could use the sort key. They're both indexed fields. And this is how, again, it stays fast and scalable. We can't query non-key attributes without doing a filter. So a filter will filter down the results after the query, meaning you're paying for all the rows you query before the filter. We want to avoid this. So, for example, if we tried to do a filter or we tried to query on the make or the model of the car, it would actually query all the rows first and then filter them after that. So we pay the cost for all the reads because we didn't use keyed attributes. So we want to try and avoid that. It doesn't really matter for small databases or small use cases, but as you start to scale, it can get very pricey and very slow very quickly. And the way that we avoid that is we use indexes. Indexes let us specify alternate key structures that we can query on to keep things fast. They give us increased query flexibility. So, we can query our database in different ways. We can avoid scans and filters, and therefore, the cost and performance hits that we would pay by using those. And the downside is that we need to pay for extra writes to those indexes. So as we write data into the table itself, it's also going to write the relevant data into those indexes also. So there's 2 types of indexes. There's a local secondary index, and they can only be used on a table with a composite primary key. And what that lets you do is specify an index with the same partition key, but a different sort key. So in this example here, we have a table with the partition key as user, and the sort key is image. But if we wanted to change the sort key to date, we could create a local secondary index to do so. And they need to be defined on table creation. Global secondary indexes, on the other hand, are a little different and a little more powerful and flexible. They can be defined whenever we want after table creation, and they can be used to specify a completely different table or key structure for the table. So in this example, we've got a table name with songs keyed by song ID. We could create a global secondary index or a GSI for the genre, and that's sorted by number of likes. Or we could create a GSI for the singer ID and sorted by the launch year. So you can see how it gives us a little more flexibility in how we query our data, and we can avoid doing those scans and filters. So a few best practices before we dive into the last example. Know your access patterns up front. Try and pre-join data and get it into a single table. We really shouldn't be spreading things amongst many tables and having to join them together. Select indexes up front if you can, and try and understand which indexes you'll need ahead of time. You should pretty much always go for eventually consistent reads. They're half the price, they're much faster. You don't have to wait for data to be, all the data to be not stale before you query it back out. We can avoid filters and scans, and you should also try and abuse IDs. Try and pack as much data into your keys as possible so you can query them in different ways without having to pay the cost of creating more and more indexes. So we're going to model a hierarchical example. And this is a very popular one with SQL databases. It's usually expressed with a bunch of joins and a bunch of different tables. So we're going to express a employee database, like a worldwide employee database. And we're going to have company, and we're going to have departments within that company, and then we're going to have offices within those departments, and finally job roles within those offices. So step one, if we were to model this with Dynamo, we need to identify our access patterns. First of all, we need to be able to retrieve a single person by their employee ID. We need to be able to gather all people in a particular company. We need to be able to gather all people from a certain department within that company. We need to be able to gather all people in a particular office within that department. And finally, we need to be able to gather all people with a certain job role in that office. So we can set about creating our primary keys based on those access patterns. First of all, we need to choose a good primary key that enables us to uniquely identify everything for writes and updates. And we want to evenly distribute our data across the partition key. So we don't want lots of keys that are the same, so we don't bunch up and get shards that are what are known as hot. So we can start off by creating a basic, simple primary key on an employee ID, and that satisfies the use case of just being able to fetch an employee by their employee ID. The next step is we need to define our indexes. So we know that we need to be able to get people by their company as well as their department, office, or role. So we can create a single GSI for this with a partition key of company and then a sort key named department, office, role. So you can see how we're starting to abuse IDs and pack in as much data as possible. We can have a partition key of company, and then we can create a sort key for department, office, and role. So engineering, Dublin, VP. So we create our index. And then this is how we start to query this out. Pretty similar to the last example. The only difference is that we have an extra key. So we are able to query our company. So we'll be able to give a company like Stripe, for example. And then we can also pass in our department, office, role. So in the first query, you can see we pass in Stripe with no sort key, and that'll just give us all the people that work on Stripe, and then their sort key will be automatically sorted. So they'll be sorted by department, office, and role automatically for us. In the second example, we query for employees who work in engineering in Google's Zurich office. So we could do that by asking for a Google partition key, and then engineering #Zurich for the engineering department and the Zurich office. And you can see in that query, we have a begins with. So company equals company and begin with department, office, role. So we can actually just check if the sort key begins with something, and it gives us flexibility around querying with a single index. Finally, we want to query an item based on not just department or an office, but job role as well. So if we wanted to fetch all the people who work in Intercom, in UX, in San Francisco as a designer, we can query that with the following, Intercom, and then UX #San Francisco #designer. So you can see we have that flexibility just from using the single index. And the powerful thing about this, as we start to query it, is that this is essentially scalable over like millions of rows. So if you had a genuine worldwide employee database, you could query them for all those things with essentially single millisecond latency. So that's very powerful, especially considering that you don't have to worry about scaling or managing any of this and being able to achieve that kind of speed fairly consistently over time. So in this example, we're just querying for Stripe, and we are looking at the engineering department and the Dublin office. And you can see here, this is how the results come back. Everyone in Dublin in engineering is listed, and the sort key just orders them by their job role. And that's it. Thank you very much for listening.
Okay, thanks very much for that. That was great. Now, as I say, for a message from our sponsors. One of our sponsors is Rapid7. They've got a talk coming up tomorrow from Arnaud Roger, I think. Don't ask me how you pronounce these things. But yes, we'll be just running a quick video from Rapid7 about what they do.